Hello everyone. So now we are starting MOS physics. Okay. So this is the part like many times student leave this part. Okay, because they say this part is from ADC, not from analog electronics, and they skip this part. But many times interviewer asks question from this part as well, and this is very typical part. Like I wouldn't say typical, but you need high level of concentration to understand this part. Okay. So we will see complete MOS physics. Okay, every aspect that can be asked, that will be cleared. Okay, so just pick your pen and paper and write down the things along with. Okay, just don't see the video, you wouldn't understand anything. You can understand the circuits uh, like that, but without using pen and paper you wouldn't be able to understand this. We won't solve any numerical here. Okay, nothing like that, no numerical, nothing like that, only the concepts. Okay, we will just see the concepts. So now we will start. So classification of MOS. So there are two kind of MOS. What is MOS? Metal oxide semiconductor. Okay, so there are two kind of MOS, N channel and P channel. N channel will have two type: depletion type, enhancement type. And depletion type and enhancement type. You don't need to mug it up, you will remember it. Okay, you will surely remember it. So N channel, P channel, depletion type, enhancement type. So we will study four kind of MOS, right? N channel depletion type, N channel enhancement type, P channel depletion type, and P channel enhancement type. Okay, so these four kind of MOS we will study. Then the second question is why we are studying MOSFET. Like now, where does this FET word comes from? FET, field effect transistor. Where does this come from? So that we will see. Okay. So what is the full form of MOSFET? Metal oxide semiconductor field effect transistor. So what is field effect transistor? That we will see. So now why do we want to build this device? Like why do we need a MOSFET? Why MOSFET? Because we need to build an amplifier, right? Because we want to design an amplifier that amplifies our input signal. Okay, so for designing amplifier you need a dependent source. You need a dependent source. Okay, there should be some source that is dependent on the input. Okay, some source that is dependent on the input and that goes to output. Okay, let me draw a diagram. Like let us assume you have this input Vi applied. Okay, and this Vi comes here. Now here you have a dependent current source. Okay, that is proportional to this input, and then you have a load at output, and this is your V0. But I should write it like this. So this is your V0. So what will be your V0 here now? V0 will be KRL K into Vi into RL and minus sign, right? Because the current is flowing in this diagram. So V0 will be K into Vi minus RL. So your V0 would be minus KRL into Vi. So your gain, now your gain can be adjusted with the value of K. You can vary the value of K and your gain will be adjusted if you want to increase the gain or decrease the gain. So this is what we want to design. So this is our target. We will make a device where the current is dependent on the input. Okay, depending on the input voltage, the current should vary. Okay, that kind of device we want to design. That's why we are studying MOSFET. So that you should know. Okay, so after this we will now see N channel depletion type MOSFET. Okay, so in the next video we will see that. Yeah, so now we will see N channel depletion type MOSFET. So this is the basic structure. This is a semiconductor device where we have N plus doping. This is metal contact. So N plus doping and metal contact. This terminal is called source. This terminal is called drain. Here also we have metal and here we have oxide here. Okay, we have oxide layer here and then we have this N channel and this is gate terminal. okay, and there is this body terminal, okay. These are metal contacts, okay. So this is the 4-terminal device MOSFET. So this is the structure. So now we will see definition one by one. So what is source? So source from where the electron enters, okay. So basically some electrons will the bias that we apply, we will apply some voltage, okay. We will apply some voltage on gate and drain, and because of that some electrons of this n plus, okay, some electrons will enter, okay. From source the electron will enter and it will travel through the channel and will get out of the drain. Electrons will enter from source, will travel through the channel and will get out of the drain. Now what will gate do? The gate will control the flow of electrons, okay. The gate voltage will control the flow of electron. How it will control, that we will see, okay. We will keep on varying the value of Vg, and that we will see how it is controlling, okay. So what did I say? From source the electron enters, travels through the channel and get out of the drain, and the gate voltage controls, and the gate controls the flow of electron, okay. So it is like a tap. So the gate, something that we move, that controls the flow of water. How much water should we have? The drain is point from where the water goes out, and the source is from where the water comes in, and this is the channel for where the water flows, okay. So this is the concept, okay. So these are the definitions, like what is source, gate controls the flow of electron, drain from where the majority charge carrier leaves, channel the path between the drain and source from where the majority charge carrier travels, okay. I should have written the majority charge carrier here, not the electrons, okay. From where the majority charge carrier enters, and gate controls the flow of majority charge carrier, because here the majority charge carrier is electrons, because this is n plus. N plus means highly doped n type semiconductor, okay. And simply n means lightly doped, or doped, lesser doped than n plus, okay. So n plus means highly doped, okay. Now what is FET? So FET is field effect transistor. So because of the field that we apply, that will modulate the flow of current, okay. So that the flow of current is modulated by the applied voltage or electric field. So whatever the voltage we apply here on gate voltage, on drain or on drain, okay. So whatever the electric field we apply, by effect of that electric field, the flow of electron will be maintained, okay. The flow of electron will be modulated, and the flow of electron is modulated, that means the current is modulated, okay. So we will see the complete analysis. You just need to know like why it is called field effect, because the effect of the applied electric field, because of the effect of applied electric field we will get the current, okay. So that's why it is called field effect transistor. So these were the basic definition. Now we will see the analysis. So for n channel depletion type MOSFET, the first condition we are taking is that we are putting VGS to be 0, okay. So one thing is also there to notice is that we will always short circuit source and body. Why so? We will surely see that, okay. Just watch the complete series, you will get to know every answer, okay. So your source and body will be shorted, okay, and we will take source as a reference voltage. Like if I am saying that I am applying VDS to be positive, like I am saying I am applying VDS to be 4 volt, then I will put VD to be 4 volt and VS to be 0. So your source and body are shorted, and both are shorted to the ground, okay. So this is our reference voltage, our source is our reference voltage, okay. So now what I am doing is that I am putting gate to 0, source to 0, and VD is positive, okay. The drain voltage is positive. Now what happens is that we need to see. Yeah, so what do you see here is that here your n plus is highly doped, right? This is highly doped, this is also highly doped, and this is less doped than this one. So N plus is highly doped. If it is highly doped, that it means that it has more conductivity, right? Why more conductivity? Because it will have more charge carriers. If it is highly doped, it will have more charge carriers and then it will have more conductivity, right? Now if it is have more conductivity, it will have less resistance, right? And N is lightly doped, that means it will have more resistance, right? So this whole thing can be replaced something like this. First we have N plus here, on the leftmost side we have N plus, right? So something like this we can show, okay? Then we have the channel, so it will have higher resistance, so we are showing it like this. Then we have again the drain side, so we are showing it like this, okay? The source size is shorted. This is RS, this is RD, and this is RCH, okay? And this is here we are applying, let us assume we are applying 4 volt at drain. This we are applying is 4 volt, okay? So now if you are applying 4 volt, this RS resistance we have, RD resistance we have, and RCH resistance we have. So RCH is greater than RS and RD. So what will happen? Here you will have 3 volt drop, let us assume. If this is 1 ohm, this will also be 1 ohm. And if RCH is greater than RS and RD, let us assume it is 2 ohm. So what will be the voltage drop? 1 volt. So RS and RD both are having 1 volt voltage drop, but RCH will have 2 volt voltage drop. Why so? Because since RCH is greater than RS and RD, it will have more voltage drop. The channel feels high electric field, right? Because it will have more resistance, then it will feel high electric field, okay? Now in N channel what do we have? So in N channel we have this, right? This is your N channel, and here you have applied this positive potential, okay? And this positive potential 2 volt is applied here. So this 2 volt will attract these electrons, okay? This 2 volt will attract these electrons. Now what will happen is that this 4 volt is applied. From here you have this, right? This you have in the channel itself, this you have, right? This positive voltage will attract these and the electron will flow in this direction. So the flow of electron will be something like this. From here it starts, okay, and electron will flow something like this, okay? Like this is not the only region the electron is getting there, okay? I will show one more region there, okay? I will show one more region. Just after this I will show one more region. So what is happening is that this 4 volt is attracting the electrons. If electron is going in this side, the current will flow this side, because the current flows in the opposite direction of electron. So there will be ID current in this direction, from drain to source, from drain to source we have ID, okay? So now what we do is that, so till this point I guess all of you have understood. The N plus is highly doped, more conductivity, less resistance. N is lightly doped, less conductivity, more resistance. So a high voltage or high electric field is generated across the N channel. So that will attract the electron and the electron will move towards the drain. So that's how the current flows, okay? So now what we will do is that, So now this is like this much region we are taking, okay, this much region. So this much region we are equating it to this, okay, like this is RCH, but let us assume RD is, if 1 kilo, take RD to be 1 volt, take RD to be 1 volt. If RD is 1 kilo, not 1 volt, 1 ohm, RD is 1 ohm, so RS will be 1 ohm and RCH will be 2 ohm, okay. So this will be 1 ohm, this will also be 1 ohm because we have divided it into 2. RCH is divided into 2, 1 ohm, 1 ohm, 1 ohm. So here we will have 4 volt, 3 volt, 2 volt, 1 volt, and this will be grounded, right, because the source is grounded, the side is grounded, so this will be grounded, okay. Now what do you see here is that here you can assume a PN junction, right, a diode you can assume, it's not there but you can assume N plus is this terminal and this is P, so a diode you can assume, right, here you can assume a diode, right, so the diode you can assume there. So now what happens is that if we go from drain side to source side, if we are going from drain side to source side, the potential is continuously decreasing. When we go from, okay, let me pause it and write it. Okay, so what I said is that when we are going from drain side to source side, the potential is getting decreased, and we can also assume a diode here, like this is N, this is P, so we can assume a diode here. So what we see here is that, okay, like this was the complete this, and this is P substrate, so I can write P substrate here, P substrate that I can write, okay. So this was N, this all was N plus N and N plus, and this is P, so we can assume a diode here. So this will have 4 volt, this will have 3 volt, this will have 2 volt reverse bias, this will have 1 volt reverse bias, okay, and this one won't have any reverse bias. So this will have 1 volt, 2 volt, 3 volt and 4 volt. So what do you see here is that when you go from drain to source side, the reverse bias is getting decreased, right. So at drain side you will have more reverse bias, okay. When you go from drain to source, the reverse bias is getting decreased, so at drain side you will have more reverse bias. If there is more reverse bias, there will be higher depletion region, right. I guess you know all these stuffs, what is depletion region and everything, because in basic diode you have studied, right. So if we have more reverse bias, there will be higher depletion region, right. So when you go from drain to source, the depletion region width gets decreases. And what is the characteristics of depletion region? In depletion region there is no charge carriers, okay, there is no moving charge carriers, okay. In depletion region there is no charge carriers, there is ions but no charge carriers. So when we are moving from drain to source side, the reverse bias is getting decreased, and the reverse bias is getting decreased, so the depletion region is continuously getting decreased. Or what you can say, when you are moving from source to drain side, the reverse bias is getting decreased, so the depletion region is getting increased. Let me see if I have drawn the diagram here. Yeah, you can see here, this is the drain side, okay, drain side. This is just the channel, the middle part, okay, N channel we are talking here. This is just the channel, only this part, okay. So this I am saying as drain side, okay, this I am saying as source side. So our main concentration is on the channel, okay. So this is the drain side and this is the source side. So at source side we have less reverse bias, and at drain side we have high reverse bias, right. So at this side we have high reverse bias. So this is the depletion region we have formed, P substrate and N channel. So depletion region will be larger, and here the depletion region will be lower, okay. So let me write it all here. Okay. So when we move from drain to source side, the reverse bias decreases and depletion width decreases. So at drain side, the depletion width is increasing. Okay. So on drain side, depletion width is increasing. And there is one more interesting thing you can see here is that, like here we will have plus, right? Because in N plus we have this, and because of the drain, this electron is gone. So only the plus is left, right? And at this side we will have this because of this PN junction. So at this side we will have this. Okay. In P substrate we will have only this because this is also gone because of that PN junction reverse bias, right? So now what happens is that because of this plus and minus, there will be one electric field. Like if this is the plus here, if this is the plus here, this minus will be here only, and because of that we will have one electric field in this direction. Okay, like this will be your N plus, this is the channel, and this is plus, this is minus, this is minus, this is plus. So we will have one electric field in this direction. Now one electron is coming from channel to this side. Now because of this electric field, this electron will go to drain. Okay, I also showed you this concept, like this drain voltage is developed across the R channel. Okay, this more drain voltage is developed across the R channel, and that's why the electron gets swept. But because of this electric field as well, this electric field is also generated here. Because of this electric field as well, the electron gets swept. So you can tell the interviewer like this. Okay, there will be one electric field as well, and because of this electric field, the electron will get swept as well. Okay, so since you are I will remove it off. Okay, yeah. So since you are increasing VDS more and more, if you are increasing VDS not from 4 volt, from 4 volt you are going to 5 volt. So if you keep on increasing the VDS, the reverse bias will get increased, right? If you are increasing the VDS, the reverse bias that I showed here, that will increase. If that will increase, that will attract the more electrons, so the current will increase. Or what you can say, if you increase this, let us assume from 4 to you are going at 8 volts. So if you are going at 8 volts, this will have R channel will have 4 volts here. If R channel will have 4 volts, it will attract more electrons, and more electrons will go, and the current will increase. Okay, so like this the current will keep on increasing. So if you are increasing the VDS value, the current will keep on increasing. Why so? If you are increasing the VDS value, the more voltage is going towards the R channel. If more voltage is going, it will attract more electrons, and more electron will flow through the drain. Okay, we will flow through the channel and goes to drain, so more current will flow. Or what you can say, the reverse bias is getting increased. If the reverse bias is getting increased, if the reverse bias is getting decreased, the depletion region is getting increased. If this is the depletion region, the electric field is more, and this electric field is attracting the electrons more with more force. If electric field is more, then it will attract the electron with more force. Okay, so that's how the electrons is getting swept away in the drain. So with the increase in VDS, the current is increasing, but there is one condition where the current saturates, and that condition is VD saturation. Why it is saturating? Let us see that. Okay, so let me write it down completely. Okay, so this is what we saw, right? The VDS increases, the potential across the R channel increases. Also, there is more depletion region, so there is high electric field, and because of that, electrons will feel more force, and the current increases. So with the increase in VDS, the current increases. But I also told one more thing. What more thing? I also told that when there will be one VDS after which the current will not increase, the current will saturate. So there will be one VDS after which the current will not increase, the current will saturate, and that point is VDS saturation or saturation voltage. Okay, so now why it is happening? So now first I was saying that if I am increasing VDS, the electric field will be more and the electron will be swept away with more force and the current will increase. Now, if you are keep on increasing the VDS, the reverse bias will also increase. If the reverse bias will increase, the depletion region will increase, right? Here VDS was 0. Now if you are increasing VDS, the VDS is continuously increasing. Let us assume VDS here was 1 volt or 2 volt. VDS here was 4 volt. VDS here was 5 volt. Let us assume that. So now if we are continuously increasing, if we increase the VDS more, let us assume we are increasing the VDS like this. Okay. So now the depletion region will be more and the channel will look something like this. So this will be your channel, right? This will be your channel. Now this will be your channel. If you have increased the VDS value, this will be your channel. Your channel width is getting decreased, so the number of electrons are getting decreased. There are two things. First thing is that the electric field is getting increased. Here this is the condition, plus minus, plus minus. Okay, this electric field is getting increased. Okay, but the number of electrons present in the channel is getting decreased. Do you get it? The electric field is getting increased. That means the current should increase, but the number of charge carriers are getting decreased. The number of free electrons that is present in the channel, that are getting decreased. So current will not increase. So the current saturates. So this is the real region. That's how you should tell the interviewer. Okay. The electric field is getting increased. The current should increase. But in channel, the number of free electrons that is responsible for the current flow, that are getting decreased. So the current, one phenomena is saying the current should increase, one phenomena is saying the current should decrease. So the current saturates. Okay, and many people would get the doubt, यार अब तो सैचुरेट ही हो गया पूरा ड्रेन साइड, तो फिर करंट कैसे फ्लो हो रहा है? सैचुरेट हो गया, लेकिन ये हाई इलेक्ट्रिक फील्ड है ना, it has been saturated, but there is this high electric field that is attracting the electrons. Do you understand? The drain side is saturated. There is no free electron, but there is high electric field that will attract the electron, and will go there. So these are very deep concept. Okay, you should be highly attentive to understand this. Okay, so I hope you have understood. We will revise the complete concept once again from 0 to whatever we have studied. Okay, so let us draw the waveform first. How it will look like is that first it will be a bit linear. Okay, then there will be some curve, sublinear region we call that, and then it will saturate. Okay, ideally it will saturate, but we will see one condition that it doesn't saturate. It increases by a small margin, but ideally it will saturate. Why it increases, what is that phenomena called, that everything we will see. Okay, so this was at VGS equals to 0 volts, right? And what are these regions called? Like this we call linear region, because the current here increases linearly, and this we call saturation region. Okay, so these things you should know. Now what did we analyze till now? Okay, yeah, this is the question written here. Why does the current saturate after VDS saturation? So I will write the answer here. So you got the answer, right? Because here the electric field is getting decreased, but the number of charge carriers in the channel are getting decreased. So because of that, one is saying the current should increase, one is saying the current should decrease. So because of that, the current saturates. Okay, yeah, so that's it. Okay, so let us revise it once again. Okay, we had this n channel depletion type MOSFET. We are studying depletion type. In depletion type MOSFET, we already have a channel present. Okay, most of you are thinking like, what is it teaching? we have studied that there are no channel and we apply some potential and then we get the channel. So that is enhancement type. We are studying depletion type. Okay, depletion type we are studying. Okay, not enhancement type. So why it is called depletion type? Yeah, why it is called depletion type? Because the channel is getting depleted of charge carrier, right? First it had complete charge carriers, dot 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 dot, complete dot, it was there. But as we are applying VDS value, the reverse bias across the drain side is getting increased. So if reverse bias is getting decreased, the depletion width is getting decreased. So our area, our channel is getting depleted of charge carriers. So that's why it is called depletion. Okay, so our channel is getting depleted of charge carriers. That's why it is called depletion. Okay, yeah. So this was your MOSFET, and these were common definitions like what is source, gate, drain, and channel. And then we saw the effect of VDS. So first VDS, most of the VDS will occur across the R channel, and that will attract the electrons. Okay. Then we saw that if we are going from drain to source side, the reverse bias is getting. If we are going from drain to source side, the reverse bias is getting decreased. Since the reverse bias is getting decreased, there is more depletion on drain side and less depletion on source side. If there is more depletion on drain side, because of that, there is high electric field that will attract the electron, and the electron will feel more force and the current will increase. But what happens is that if we keep on increasing the drain voltage, if we keep on increasing the VDS value, at some VDS value, the drain side will be completely depleted of charge carrier. The drain side will completely be depleted of charge carrier. After that, the current will not increase. Why so? Because now the channel will start having the lesser value of charge carriers, right? Because the channel width is getting decreased now. Before that, the channel widths were at least complete, but now the channel width is getting decreased, so it will have very less charge carriers and more electric field. So that's why the current will saturate. So that's the complete explanation. Now I will write here why the current saturates. Just whatever I have told, that I will write. Okay. So now we will see the next condition. There we will apply the VGS value negative. Okay, and VDS the same. We will vary the VDS value like this, and we will apply VGS value to be negative this time. In this condition, VGS was 0. There was no effect of gate voltage. Now we will see the effect of gate voltage as well. Okay. Yeah. Thank you. Hello everyone. Now we will see the condition 2. Okay. So in this one, now the VGS value will be non-zero. In the previous analysis, we saw that the VGS value was 0, and we saw the complete analysis. Okay. Now the VGS value is non-zero. Okay. So your VGS value is negative now. So I am putting source to the ground because I told that I am taking it as a difference. Okay. Now your gate voltage is negative and your drain is always positive. In the previous video, I forgot to tell you why I am taking drain as positive. Okay. Because I can't take drain as negative. Because here the majority charge carrier are electrons. Okay. Majority charge carriers are electrons. Here the majority charge carrier are electrons. So if I take drain to be negative, then it will repel it, right? The negative charge will repel it. So it will have a repulsive force. So drain voltage has to be positive. If drain is negative, there is no current flow. So that analysis we are not doing. We are taking drain as positive so that the current flows. Okay. So now since your gate is negative, this potential is at negative. Now what will happen is that this is the N channel. Now I am not forming the complete MOSFET here. I am just forming the channel. Okay. Just this part I am forming. Okay. Just the channel. So if this is negative, in N channel we have this plus and then this electron. These are the charge carriers. Electrons are the charge carriers. Because of that, the current is flowing. Because of the charge carriers, the current is flowing. So if this is negative, these will go down, right? These will go down. And here we have what? P substrate. So in p substrate we are having this, right? So these will go up. So both holes and these electrons are getting recombined. Look, the VDS is positive. The what work it will do, that we have already shown. The increasing the depletion region, all that work we have shown. We have already studied. If VDS is positive, what will happen is that in the drain side there will be more depletion region, and because of the more depletion region, the current will flow and the electron will get attracted. That we have already seen. Okay, but since we are applying negative voltage to the gate, because of that negative voltage, the channel is getting depleted of charge carriers. Because of the negative voltage applied, the channel is getting depleted of charge carriers. Since the channel is getting depleted of charge carriers, so if we keep on increasing the negative value of gate, we will get lesser amount of current. Do you get it? Look, that drain voltage is positive, that will do the same work. Okay, it will increase the depletion region from the drain side and it will attract the electron. But the electron are getting less. The electron itself are getting less. The charge carriers, which are electron, are getting less. They are getting recombined with the holes. So if the charges are getting less, so the channel is getting depleted of charge carriers. So if the channel is getting depleted of charge carriers, the current will decrease, and there will be one point at which the channel will be completely depleted of charge carriers. The channel will completely be depleted of charge carriers. There will be one point where the channel will completely be depleted of charge carriers, and that point is known as pinch off. Okay, so many people get confused with pinch off, like the thing that I told you, VDS saturation, na? This VDS saturation. Many people, even I have seen the teachers teaching like this is the saturation voltage. This is the pinch off voltage. This is not the pinch off voltage. The pinch off voltage is the value where the pinch off voltage is the value of gate voltage where the complete channel is getting depleted of charge carriers, while the saturation voltage is the voltage where the drain side is getting depleted of charge carriers. Do you understand? What is saturation voltage? In the previous video, in the previous analysis, we saw that in saturation region, the drain side was getting depleted of charge carriers. But in this analysis, we have seen that this is a vertical electric field, right? Vertical electric field from upward to downward. The complete channel is getting depleted of charge carriers, and this vertical electric field is like constant in the complete N channel, like this. But when we are talking about drain, it has more potential here, less potential here, less potential here, less potential here. So it was asymmetric, but this is symmetric. The complete channel is getting depleted of charge carriers. And if we keep on increasing the gate voltage value, if we keep on increasing the negative voltage of gate at one potential, it will completely be depleted of charge carriers, and that potential is known as pinch off voltage, and this phenomena is known as pinch off. Okay, so now I need to write it completely. Okay, so here you can see is that when Vg is negative, the channel start getting depleted of charge carriers and the current decreases, and at some negative value of Vp, at some negative value of VGS, the channel is completely depleted of charge carriers. This voltage is called pinch off voltage. Okay, so like if this was your VGS equals to 0 volt, then it would have been your VGS equals to -1 volt, and it would have been your VGS equals to -2 volt, and this would have been VGS equals to Vp, right? And the Vp value will be negative, right? And if the current is getting less, it will saturate at lower point as well, right? If the current is getting less, it will saturate at lower point, right? So the saturation point of this curve is here, saturation point of this curve is here, and saturation point of this curve is here. So if we go like this is the saturation point, right? After that we have saturation region. After this we have saturation region. After this point we have saturation region. So this complete show the saturation region, right? And this is the linear or triode also they call it. Okay, so this is triode or linear region, and this one is saturation region. Okay, so that's the analysis for VGS equals to positive. Now we will see VGS equals to, that was the analysis for VGS equals to negative. Now we will see the analysis for VGS equals to positive. Now we have applied gate potential to be equals to positive. Now what happens is that now this is positive and this is n channel. Okay, so these electrons will get attracted, right? Like it will remain at this plus charge only. Okay, like it will get attracted, but what will mainly get attracted is that these minority charge carrier from P substrate. Okay, look, what drain does is that, what drain potential does? Drain potential increases the reverse bias at drain side and gets the depletion region. Let us assume he got 1 plus, okay, and we have, yeah, he got 1 plus here. Okay, because of the drain potential, we get reverse bias, right? Reverse bias and depletion region like this. So we get many plus, but they don't have any charge carrier, right? They don't have any charge carriers. Okay, now what will happen is that this P substrate is having some minority charge carriers that are electrons. P substrate is having minority charge carrier that are electrons. Now these electrons will get attracted by this potential. They will get attracted by this potential, and now this is just a positive ion. It doesn't have any electron. So this electron will go to this positive ion. Do you get it? This electron will go to this positive ion. Okay, so by like this, there will be many positive ions because of the drain potential. So they will go. So in the channel, the majority charge carrier increases. Also there is some reverse bias as well, and because of that the electron will get attracted and the current will increase. So because of the positive potential applied, the majority charge carrier in the channel is getting increased and the current increases. Okay, so that I need to write. Okay, so that's that is what I write. VDS is positive, then the positive ion gets an electron from P substrate, and P substrate is having minority charge carrier as electron. So these electrons come there, and the channel will have more charge carriers. Now the current will increase. So that's what we write. Okay, so here what we can see is that that is the complete output characteristics. Okay, complete output characteristics. So let us assume this is VGS equals to 0 volt. This will be VGS equals to minus 1 volt, VGS equals to minus 2 volt, and VGS equals to VP. Okay, and this would be VGS equals to plus 1 volt, and again you can increase more and the current will increase. Okay, so this is the complete characteristics. This is the output characteristic, ID versus VDS, output current, output voltage. Okay, so this is the complete characteristics, and since the current is increasing, then the saturation point will be the more. Okay, if this is VA, this is VB, this is VC, and this is VD, so VD will be greater than VC, will be greater than VB, and will be greater than VA. Okay, so if the current is more, the saturation point will be more. So this region is called linear region, and this region is called saturation region. Now what you see here is that here your channel is getting enhanced, right? The channel is getting enhanced of charge carriers. The channel is getting enhanced of electrons or the charge carriers, and here your channel is getting depleted of charge carriers. So this region is called depletion region. When VGS is negative, your channel is getting depleted of charge carriers. So this is depletion region, and this is enhancement region. So this region, this complete region is enhancement region, and this complete region is depletion region. Okay, so that's the complete characteristics. Okay, when VGS was 0, only VDS was applied. We saw the analysis how the current increases at certain point, the current saturates. Why so? because after increasing more VDS, the channel length gets reduced. If the channel length is getting reduced, the charge carriers are getting also reduced. Okay, electric field is getting increased, but the charge carriers are getting reduced, so the current saturates. When VGS is negative, the channel is getting depleted of charge carriers, so the current decreases. When VGS is positive, the channel is getting enhanced with the charge carriers, so the current increases. We are studying what? We are studying N-type depletion, N-channel depletion type MOSFET. This is depletion type. In depletion type, you can have enhancement region. Okay, in depletion type region, you can have enhancement region. Okay, in depletion mode, in depletion type of MOSFET, you can have enhancement region and depletion region as well. Okay, we haven't studied enhancement MOSFET yet. That is the most important part that I know. But from depletion type of MOSFET, they can also ask the question. Okay, the enhancement one is most important. If you know the depletion one, you will know the enhancement one in a second. Okay, it won't take any time. Now you have studied the N-channel depletion type MOSFET. Now you can analyze any kind of MOSFET. Okay, so this was the output characteristics, and this is ID versus VGS. So we can call it transfer characteristics. So ID is the output current and VGS is the input voltage. So transfer characteristics. How it is output current, input voltage, that we will see. Okay. Okay, so this is the transfer characteristic ID versus VGS. So when you increase the value from VP, that is some negative value, if we increase the VGS, the current will increase. But before VP, there is no current. So before VP, the current will be always 0. Okay, so that's the characteristics. Okay, ID versus VGS. Okay, so that's it. That's the complete analysis for N-type. For N-channel depletion type MOSFET. Now we will see some definitions and some important point. Okay, so that we see in the next video. Okay, thank you. Yeah, so now we will see some definitions, some common definition for N-channel depletion type MOSFET, that is written there. Okay, so you can't see, I guess. Okay, so first is saturation voltage. So what is the saturation voltage? The voltage, the value of VDS, the value of drain to source voltage at which the drain side of the MOSFET gets depleted of charge carriers. Okay, the value of VDS at which the drain side of MOSFET is getting depleted of charge carriers, that is saturation voltage. And now what is saturation voltage? Saturation voltage is always equals to VGS minus VT. That you should remember. Okay, the applied value of VGS minus VT, that is the saturation voltage. Now what is VT, that we will tell. So VT is the threshold voltage, and what is pinch off? VP. So what is pinch off? At some value of VGS, at some negative value for N-channel depletion type MOSFET, at some negative value of VGS, the channel is completely depleted of charge carriers. Okay, at some negative value of VGS, the channel is completely depleted of charge carriers, so there is no current flow. So that potential is known as pinch off voltage. Okay, and what is threshold voltage? The threshold voltage, I am not writing it here, you can simply write it. Okay, I have told the definitions. For pinch off, I will also again tell. Okay, so what is pinch off voltage? At some value of VGS, at some negative value of VGS. Negative value of VGS, that line is appropriate only for N-channel depletion type MOSFET. So you will say in N-channel depletion type MOSFET, for some negative value of VGS, the channel is completely depleted of charge carriers, and at that point there is no current in the MOSFET. Okay, so that potential, that negative potential of VGS is known as pinch off voltage. Now what is threshold voltage? So what is threshold voltage? The minimum value of VGS that is required for the drain current to flow. Like the minimum value of VGS at which the drain current ID flows. Okay, so for depletion type MOSFET, VT and VP are same. Right? For depletion type MOSFET, VT and VP are same because the minimum value of VGS at which the current flows. What is that? That is the pinch off voltage. The minimum value of VGS, after that the current flows. So that is pinch off voltage. These definitions are for N-channel depletion type MOSFET. Okay. You will say I am saying the definitions for N-channel P-type MOSFET. Sorry, N-channel depletion type MOSFET. So the interviewer will just ask like what is pinch off voltage? Define. So what you will say for N-channel depletion type MOSFET, this is the pinch off voltage. Okay. What is threshold voltage? That you will define. Okay. So these are the three definitions. I hope you have understood. And VT and VP are same for depletion type MOSFETs. Okay. So now for depletion type. Okay. So now there are these conditions. When VGS is less than VT, I just told you if VGS is less than VT, that means MOSFET is off. Right. I didn't show the cutoff region here. Yeah, this is the cutoff here. The MOSFET is off, that means it is in the cutoff region. Okay, so there are three regions basically. If VGS is greater than or equals to VT, that means MOSFET is on. Okay, so there are two possible regions here, right? One is linear and one is saturation. So by following this condition, first is that VGS should be greater than VT. Then after that, if VDS is greater than VGS minus VT, I have told you what is VDS saturation. That is VGS minus VT. If that is greater than, if VDS is greater than VGS minus VT, if this is VGS minus VT, if this VDS is greater than VGS minus VT, the current will be saturated. So this will be saturation mode. Okay, if VDS is greater than VGS minus VT or equal, you may say, that means it will be saturation mode. If it is less than VGS minus VT, it will be linear mode. Okay, so I hope you have understood it. I have put equal here. Equal shouldn't be there. Okay, now one more thing I need to write. I will write here only. For N-channel depletion type MOS, okay, VT and VP are negative, right? VT and VP are negative. Okay, VGS can be positive or negative, anything it can be, right? At positive we have current, at negative also we have current, right? At negative also we have some current, right? So VGS can be positive or negative, and VDS has to be positive, right? The VDS has to be positive, otherwise the current will not flow. So that's the complete analysis of N-channel depletion type MOSFET. Take your time, revise it again, just see the lectures, see the class notes that you have made, the class notes that I have given, the handwritten notes that I have given, just see those, just revise it completely, you will feel very good after that. Okay, so I hope you have understood the concept very nicely. Okay, so that's it about the N-channel depletion type. Okay, now in 10 to 15 minutes analysis, we will see the P-channel depletion type MOSFET, because it will be the complete same analysis. I will just tell like what will happen and you will just draw the characteristics and everything. Okay, you can try drawing the characteristics by your own. Okay, now we will see the P-channel depletion type MOSFET. Okay, thank you. So now let us look at the P-channel depletion type MOSFET. Okay, so just as the N-channel depletion type MOSFET, here we had n plus here and n channel. So we will have p plus here, p channel, and p plus here, and we will have n substrate. Okay. So what will be the majority charge carrier here? In the n channel depletion type MOSFET, majority charge carrier were electrons, and here what will be the majority charge carriers? It will be holes, right? So here we will have majority charge carrier as holes. So like let us assume this is one hole here. Okay. So now what will we apply at drain potential? Positive or negative potential? If we apply the positive potential, it will repel the hole, right? The hole will get some repulsive force. So we can't apply positive potential. So we have to apply negative potential so that it attracts the hole and the current flows. So VDS we apply will be negative, and VGS and we will vary the VGS value. First we will apply VDS negative and VGS we will put VGS 0 and see the analysis. Then we will apply VDS always negative. Then we will see VGS to be positive and VGS to be negative. Just as the previous analysis, nothing different. So it will be in just one 20 or 25 minutes video, we will cover everything about P channel depletion type MOSFET. Okay. So now what is the condition? Now your VGS is 0 and your VDS, I can make it here, make something like this. This is 0, this is grounded. Okay, this is also grounded, and this is at negative potential. Okay, source, gate, and drain, right? And this is the channel P plus and P plus. Now what will happen if we increase the VDS in negative direction? If we are increasing the VDS in negative direction, what will happen here is that this is the diode like this, right? What am I doing? Yeah, this is the diode like this. Here we have N substrate, right? So this is P and this is N, this is P and this is N. So if you increase the negative voltage, the reverse bias will get increased. The drain side will have more reverse bias, right? Because we saw in the previous analysis why drain side has more reverse bias. So drain side will have more reverse bias. The channel will start getting depleted from drain side. Okay, but if we keep on increasing the VDS value, more voltage will occur across the channel. Also, there will be high electric field that will attract the holes, and the current will keep on increasing. After a certain VDS value, the channel will completely be depleted from the drain side, and that point is called saturation point, because after that the current doesn't increase, it saturates. So all this analysis we have already seen. I don't need to write it, I don't need to explain it once again. I will just say it once more. So what happens is that we are applying VDS to be negative. If we keep on increasing the VDS value in negative direction, the reverse bias increases from drain side. If the reverse bias is increasing from drain side, the depletion region is getting increased in drain side. Because of that, the holes feel a high electric field. And gets attracted to the drain side, and the current increases. Also, because of the high VDS value, there is high voltage across the channel, because the channel has higher resistance. So this high voltage across the channel increases. This high voltage across the channel attracts the electron, and the current increases. But at a certain value of VDS, at a certain negative value of VDS, the channel gets depleted from drain side completely. From drain side, the channel completely gets depleted, and because of that, there is no further increase in the current. And that point is called saturation point. So at a certain negative VDS value, the drain side of channel gets completely depleted of charge carriers. After that, the current saturates. Okay, so this is the definition of saturation voltage. So I hope you have understood it. I will just draw the characteristics now. Okay, so just keep on increasing. Then it saturates. Right, this was for VGS equals to 0 and add some value and this value. This is the saturation point, this VDS saturation. Okay, so that's the analysis. Right, now what we will see here is that we are applying VGS greater than 0. Okay, so this is the gate voltage. This is positive with respect to the source. Source is at ground. Now we are only forming the channel. Okay, we are interested in this part only, just the channel. Okay, so we have just formed the channel here only. Okay, so if we are applying positive voltage here, this hole will get repel. Right, this hole will feel a repulsive force and will go downwards. Right, so your channel is getting depleted of charge carriers. VGS is positive, channel getting depleted of charge carriers. Channel is getting depleted of charge carriers, the current decreases. In case of n channel depletion type MOSFET, if we were applying positive voltage, the electrons were getting attracted, so the charge carriers were getting increased in the channel. Now the channel is getting depleted of charge carriers because of the positive voltage, because this time we have P channel, so the channel is getting depleted of the charge carriers, so the current decreases. Okay, now in case of VGS negative, VGS value is negative, so we are applying negative potential here. Okay, so in this case there is n substrate. N substrate have majority charge carrier as electrons but minority charge carriers as holes. In n substrate we have minority charge carriers. Right, these minority charge carriers are holes, and here we have drain. Right, this is drain which is already at negative. Right, and this source is so this VDS value of this negative value of VDS will form a negative ion, right, because it will take up the holes. Right, it will take up the hole and will form a negative ion. Like this they were forming the depletion layer. Right, so this negative value of VDS is forming a negative ion. Now what is happening is that because of this negative charge, this hole is getting attracted and this hole will go to this negative ion here. Okay, because of that negative charge, the hole is getting attracted and the negative ion that has been formed by the VDS value, that will get the hole. So apparently what is happening is that our charge carriers are getting increased in the channel. Right, the charge carriers are getting increased in the channel. Okay, so channel is getting accumulated with charge carriers. Okay, or getting enhanced with the charge carriers. So if we are applying VGS to be negative, if we are applying a negative potential at gate, we are attracting the holes and the channel is getting enhanced with the charge carriers, so the current will increase. So now this is what we will write, but I will just show it like this way. These are going upwards. Okay, so if VGS is negative, channel getting enhanced with charge carriers and the current increases. Okay, so this is the form. Okay, so now this is the output characteristics, right? First, this is the linear region, it increases. If we have negative voltage, the current will increase. If we have positive voltage, the current will decrease. So this one is enhancement mode. Enhancement mode. And this one is depletion mode, because in this one the channel was getting depleted of charge carriers, and at some negative value of and at some positive value of VGS, at some positive value of VGS, we'll write it with some pen. At some positive value of VGS, some positive value of VGS, the channel is completely depleted of charge carriers, right? At some positive value of VGS, the channel will be completely depleted of charge carriers, and the current becomes 0, right? And the current becomes 0. That potential will be called pinch of voltage. So some positive value of VGS, so that is VGS equals to VP. So this is the cutoff region. Okay, this is the cutoff region. Okay, so in cutoff region, at some positive value of VGS, the current completely gets to 0. The current is 0, right? So this is what we call cutoff region, or this potential is known as pinch of voltage. Okay, so in this one, what did you understand is that here the pinch of voltage is positive. In the previous one, the pinch of voltage was negative. In the previous one, if VGS was positive, we were getting high amount of current, and if VGS was negative, we were getting less amount of current. In this one, in P channel 1, if VGS is negative, we are getting high amount of current. If VGS is positive, we are getting less amount of current. You don't need to mug it up. You will just think about it. Like if they are talking about N channel, okay, N channel we have. In N channel, we have positive and one electron there. If we are applying positive voltage, the positive voltage will attract the electron. If they are attracting the electron, the current will increase. So for VGS greater than 0, the current will increase. If we are applying the negative voltage there, negative and the electrons, it will repel each other. If the negative charge will repel the electron, the electron will feel a force downwards. So the channel is getting depleted of charge carrier, the current decreases. Okay, what is saturation? At a certain point, at a certain voltage of VDS, at a certain, if you are talking about saturation voltage in N channel, saturation voltage in N channel. So at a certain positive value of VDS, the channel gets depleted of charge carriers from drain side completely. After that, the current saturates. So that point is known as saturation point. Okay, or the value of VDS is known as saturation voltage. And for P channel depletion type MOSFET, at some negative value of VDS, the drain side of channel gets completely depleted of charge carriers. After that, the current saturates. So that point is known as that voltage is known as saturation voltage. Okay, so these are the saturation voltage. Okay, and if the current is less, then it will get saturated at less voltage as well. So this is the saturation point of this curve. This is the saturation point of this curve, and this is the saturation point of this curve. This is the saturation point of this curve. Here this and this. So this line we have made. So before that linear, after that saturation. So I hope you have understood it completely. Right? Now we will see the transfer characteristics. So if we are increasing the value of VGS, okay. So if we are applying the negative value of VGS, we will have some current. Surely we will have some current. But at positive value of VGS also we will have some current. But after a certain positive value of VGS, we will not have any current. Right? Because if we are applying VGS to be positive, the channel is getting depleted of charge carriers. If the channel is getting depleted of charge carriers, the current decreases, and at some point it goes to 0, and that point is known as pinch off. Okay, so these definitions I don't need to say those definition again. Okay, I don't need to tell those definition again because I have told it many times. So you can write it down by your own. Okay, and just if the interviewer asks like what is pinch of voltage, then you have to be sure that for what kind of MOSFET you are saying. Okay, so if we simply ask what is pinch of voltage, then you will say for N channel depletion type MOSFET, this is the pinch off. For P channel depletion type MOSFET, this is the pinch off. Okay, so that's how you should answer. Okay, so this is the pinch off voltage, and what is threshold voltage? The threshold voltage will be the maximum value of VGS at which the current flows. The maximum value of VGS, after this VGS value, the current doesn't flow, right? So the maximum value of VGS at which the current flows in the MOSFET, in the P channel depletion type MOS. Okay, so the maximum value of VGS at which the current flows, that is known as threshold voltage. Okay, so you can see these conditions. If VGS is greater than VT here, or VP you can say, because pinch off and threshold are both same in case of MOSFET, right? So if VGS is greater than VP, the MOSFET is off and it will act as in cutoff region. Okay, so what was VT? The maximum value at which the current flows. After that, the current doesn't flow. Okay, now if VGS is less than VT, the MOSFET will be on and it will work in two region, linear and saturation, right? So there are two region, linear and saturation. So when will we have saturation region? If VDS is less than VGS minus VT. Here you can see this is the saturation point, right? So this is VGS minus VT, right? If VDS is, look, we are not talking about the magnitude. Okay, we are talking about the value. Yeah, so what I was saying is that we are not talking about the magnitude here. We are talking about the complete value. Look, this region is lesser than VGS minus VT, right? And this is greater than VGS minus VT. Let us assume VGS minus VT is minus 3. So this will be minus 4 and this will be minus 1. So this is lesser, right? Minus 4 is lesser than minus 3. So if your VDS is lesser than VGS minus VT, then the current saturates, right? So if your VDS is lesser than VGS minus VT, so saturation region. If your VDS is greater than VGS minus VT, linear region. Okay. And for P channel depletion type MOSFET, you can see VP and VT are positive, right? And VDS is negative. Okay. So VGS positive and VGS okay. VP and VT are positive, VDS is negative, and VGS can be both positive and negative. But after a certain value of positive value of VGS, the current doesn't flow in the MOS. Okay. So, but there can be current for both VGS positive, both VGS negative, also for VGS 0. Okay. Even if there is no VGS, there can be some current if you have applied the VDS potential. Okay. So this is the case. So I hope you have understood it. Okay. So this is the complete analysis of P channel depletion type MOSFET. Now we will see if the depletion type MOSFET can be used as an amplifier. So in depletion type MOSFET, can we use it as an amplifier? So that analysis we will see in next video. Okay. Thank you. Yeah. Hello everyone. So now our question is that why can't we use depletion type MOSFET as an amplifier? Okay. So in the very starting, in the first video only, what I told you, why we are making the MOSFET, to make it as an amplifier. So in this we need to have a certain input value, and there should be a dependent source, whether it is current or whether it is voltage. Let us take a current source. Okay. So depending on this input voltage, there should be a dependent current source. Okay. Then we can magnify the output voltage based on the K value. Okay. Based on this constant value. So there should be a dependent source, the source should be dependent on the input value. But in case of depletion type MOSFET, what we see here is that Even if you have VGS equals to 0, look, the gate side is input, okay, and the drain side is output. Why it is output? Because the current is getting out of the drain, right? And the direction of current is this one in N channel depletion type MOSFET. In P channel depletion type MOSFET, I forgot to tell you the direction actually. Yeah, so the holes are going in this direction, right? So if the holes are going in this direction, holes, right? If the holes are going in this direction, so the direction of current will be this only. Direction of current from source to drain. Source to drain. And in the previous one, the electrons were getting towards the drain, so the direction would be drain to source. Did I show it somewhere else? Okay, from drain to source, that I have already written, so no need to show it here. Yeah, so what I was saying is that why we are building an MOSFET to make it as an amplifier, and for amplifier we need to have a dependent current source that is dependent on the input. But what we are seeing is that even if there is no VGS applied, okay, so we will simply go to the characteristics. Okay, even if the VGS is 0, we are having some output current. Even if the VGS is 0, we are having some output current. So your output is not depending, your output current is not depending at all at input. Your output current is not depending on input at all, right? If VGS is 0, then also we are having some current. If VGS is greater than 0, we are having some current. If VGS is less than 0, we are having some current. But even if you have don't applied any input, that means if you have don't applied any VGS value, then also you will get some output, right? But we don't want that. We want our output to be dependent on the input. So whatever the current flows, that should be dependent on the input value of VG. That should be dependent on the input value. And what is input? Input is VGS, because the input is VGS here, and we are getting output at drain side. So at gate side, source is the reference, right? Source we are getting grounded. So at gate side we will apply some potential, and we will have some output at drain side. I said the source is controlling one. So here the source is, yeah, the source is the controlling one. But even if there is no source voltage, then also you are having some output. So that is not desirable, right? Now we will have to find some MOSFET where the output voltage should depend on the VGS value. Like if there is VGS value lesser than something, then the current will not flow. And then like if VGS is 0, then there shouldn't be any current flow. If VGS is negative or positive, so that analysis we will see. So for that we use enhancement type MOSFET. So after that we will study enhancement type MOSFET. So now this you have understood is that in depletion type MOSFET, even if there is no VGS, there is some current flowing in the MOS through the drain terminal. It means even if we have applied no potential at the input gate terminal, there is some output, there is some current flowing in the MOS, and we can get some value of output at load. Okay, so that's why the depletion MOSFET is not ideal for amplifiers. So now we will study enhancement type MOSFET, and we will see why it is ideal for the amplifiers. So most of you have studied the enhancement type MOSFET in very deep manner, but not the depletion type one. So you have to study the depletion type one deeply as well. Okay, now I haven't told why do we use enhancement type for amplification. I have just told that why we don't use depletion type for the amplification. Okay, now time for the enhancement type one. Okay, now we will see enhancement type MOSFET. Okay, thank you. Hello everyone. So now we will see enhancement type MOSFET. Okay, so we have already seen depletion type MOSFET, and in that we saw N channel and P channel, both kind of MOSFETs, right? Okay, now we will see N channel enhancement type MOSFET. We call it NMOS2. Okay, N channel as enhancement type, we can call it NMOS. Okay, So this kind of structure we have. So this is similar as depletion type, but what is the difference? Here we don't have N channel, right? In depletion type we already had the N channel, but here we don't have N channel, right? In depletion type, like here we have P channel, but this is not there in this case. Okay, so what we can do, how we can get the current, and how we can make it to work as an amplifier, right? Because in the previous part we studied that depletion type MOSFET cannot work as amplifiers, so enhancement type can work as amplifier. So how we will do that, we will see. So how will we start? We will start applying some voltage, okay, across gate and drain, because I have already told you that source and body are short circuited and they are taken as a reference, so both will be grounded. So at body and drain we will apply some potential and see what happens. Okay, so the first condition is when VGS and VDS both are 0, these both are grounded, so no voltage, nothing, zero current, right? If both VGS and VDS are 0, so there is no voltage that can attract the charge carriers. So nothing can attract the charge carriers, so zero current. The condition for current to flow is that the electron should get out of the source terminal, right? The electron should get out of the source terminal and walk through the channel and get into the drain terminal. That's the condition. Walk out through the source, travel through the channel and get out of the drain. That's the condition, right? So no potential is applied, so no potential, no voltage or no electric field to attract the electrons, so no current will flow. So ID is 0 ampere. Now your VGS is 0 and VDS is positive. This time your VDS is 0 and VGS is positive. So the question is, now what will happen? Okay, so now what we have is that here this is the case, right? Because this is the P substrate and we don't have N channel. In this one we don't have N channel. Now if this is this, right, and this is this, then they will already form a depletion layer, right? They will already form a depletion layer. So it will be something like this, this depletion layer will be there, right? This depletion layer will be there. So there will be one electric field in this direction and there are holes here. Okay, electric field is in this direction and holes are there. So the hole will feel a force, right, and it will go this direction. So that is working fine. The hole is uh, the hole is being attracted by the electric field, but the thing is that we have positive voltage here. We applied negative voltage at drain. We are taking the same condition that we took in the depletion type MOSFET. VDS equals to positive and VGS equals to 0. We are doing that same. In depletion type MOSFET, we already had the N channel there, right? So in N channel, what was the majority charge carrier? Electrons. So first electron was attracted by the electric field. Then at drain we had a positive voltage. So that positive voltage could attract the electrons and the current was flowing. This was the case of depletion type. In enhancement type, there is this electric field, right? Electric field is there. Now this time majority charge carrier is holes. So this will get attracted. But here we have applied positive potential. So now this positive potential cannot attract the holes. Do you understand? This time we have the positive potential. So these positive potential cannot attract the holes. So current cannot flow. So the current will be 0. Okay. So VDS equals to positive depletion layer is formed. Okay, depletion layer is formed near drain. Okay, electric field is there. Holes are getting attracted. Okay, holes are getting attracted, but since VD is positive, holes cannot go to drain terminal. Okay, so that's why the current is 0 ampere. Okay, so I guess that is fine. VDS is positive, depletion layer is formed, the electric field is there that can attract the holes, but since VD is positive, so that cannot go into the drain terminal. So the current cannot flow. The holes didn't get the complete path. If they had get the complete path, the current would be there. Now the question comes, some student may think that what if the drain is negative? Then the first thing will not happen. The depletion layer will not be formed. If VDS is negative, if the drain is negative, this is N, this is P. It will become forward bias. Okay. This is N, this is P. It will become forward bias. The depletion width will get very less, and there will not be high electric field that can attract the electrons. Okay. So we don't apply VDS to be negative as well. Okay. So that I haven't written in the condition, but I have told you. Already. Okay. We can't apply VD to be negative. So now what we do is that, if you are studying it for the first time from me, then you would think like we need to form a channel. But I am telling you why we need to form the channel. Okay, why we need to form the N channel. We already have a P channel. Why can't we have a current with P channel? That I am telling you. Interviewer may ask you question. Like, why do you really need to form the N channel? From P channel, why can't you get the current? So these are the reasons. VDS equals to negative will not work, VDS equals to 0 will not work, VDS equals to positive will not work. So now what we need to do? So now what we will do is that we will try now this thing, like if VDS is 0 and VGS is positive. If drain voltage is 0, you know the current is 0. If there is no drain voltage, there is no chance the current will flow. That is certain. If there is no drain voltage, then what will attract the electrons to the drain terminal? Okay, or the charge carrier to the drain terminal. The charge carrier has to go into the drain terminal, and for that there has to be some potential, be it positive or negative, but there has to be some potential. If there is no potential on drain, if we are talking about N channel, be it depletion or be it enhancement. If there is no positive voltage on drain, there is no chance that the current will be flowing. Okay, so VDS has to be positive. Okay, so the current is 0. But what happens if we just apply the VGS equals to positive? So what will happen, that we need to see. So VGS is positive with respect to, you may say, ground or body. Here the body is shorted. Okay, the body is at 0 potential only. Gate is at positive potential. Let us assume if it is 5 volt, then gate is at 5 volt and body is at 0. But to make you understand the stuffs, I am making like this. Okay, so from battery's negative terminal, electron will flow, right? Electron will flow like this from battery's negative terminal, right? Electrons are flowing like this. Now the electron will go inside the P substrate. Now what will happen is that they will go here. So what they will do, they will first form a depletion layer of negative charge. They will first form a depletion layer of negative charge. Why I am calling it depletion? Because there is no charge carriers. These electrons will recombine with these holes and neutralize this, like this we have, and this electron will go and will neutralize this. So what we will get? Simply a negative ion. So a layer of negative ion will be formed. If we increase VGS more, so these have been neutralized. Now there are more electrons. Now, yeah, what I was saying is that let us assume this is neutralized by this. Now there are more electrons. Now what will happen is that they will go and form a layer of electrons here. Okay, these will go and form a layer of electrons. Okay, so when VGS is positive but less than some value VT, then your channel will look something like this. This is your channel. Electron from negative terminal of battery. What should the language we should write? Gets into the semiconductor. Gets into the substrate. Actually, in the written notes, you will get some different kind of theory. Like I can't write the same theory again and again, right? So here I am writing a bit different theory, and then in the notes you will get a different words. The concept will be same, the words will be different. Okay, we'll get into the substrate. Okay, when VGS is less than VT, VGS is less than, this is some threshold voltage value. Okay, that we saw in depletion time MOSFET. This is some threshold voltage value. So if when VGS is less than VT, the channel will have a depletion layer of negative charge. Channel will have depletion layer of negative charge. Okay, can we move on to the next one? And when VGS is greater than VT, this is how your channel will look like. Like it will have these, but it will have the charge carriers too. Okay, it will have these as well, but it will have the charge carriers. These electrons will get accumulated near the, we can say accumulated. These electrons will go near the oxide layer. In the channel near the oxide layer, we will have some electrons, but the current will not flow. Now what we have done is that we are making the P substrate look like an N substrate. Like in the P substrate, we are making an N channel. So we are inverting the P substrate. So this layer is called inversion layer. Inversion layer is formed. Okay. If VGS is greater than VT, some electrons are getting accumulated near the oxide layer, in the substrate. So the P channel is looking like an N channel. So the inversion layer is formed. Do you understand this point? Now you need to attract these electrons. So what will you do? You will apply positive potential at the drain. Positive potential at the drain will attract these. The positive potential at drain. What will that do? That will uh, that will form a depletion layer between N plus and P substrate near the drain region. That will have some electric field and that will attract the electrons. The same concept that we studied in depletion time MOSFET. But in depletion time MOSFET, we already had the N channel. Okay, but in this one we made the N channel by our own. Okay, we applied some potential on gate and that potential made the N channel there. Now we are applying some positive potential on drain, so that will attract the electrons. Okay, and the current will flow. So this is the complete concept. Okay, so again now we have two conditions: VGS less than VT and VGS greater than VT. So here also the electrons are going in. Okay, electrons are there, electrons are going in. So first it will neutralize, then there will be some layer formed. Okay, so better we should make it something like this. So these are getting neutralized by the electrons, okay, and this inversion layer is getting formed. And channel we can call it. And channel it is, okay. So the N channel is getting formed. Inversion layer, okay. So when VGS is less than VT, only this condition is there, right? VGS is less than VT, then only the positive ions are, only the negative ions are there. There are no charge carriers, so the current will be zero, right? But in this case, these are already neutralized, but charge carriers are also there. These charge carriers are also there, okay. So the current will be greater than zero this time, and electron will feel the force, these electrons, okay. And if VDS is there, so this is positive and this is negative, so we have an inside electric field in this direction. So in which direction electrons will feel the force? Opposite to the electric direction. So opposite to the electric direction means what will be the trajectory for the electrons to flow? So they will come like this, goes like this, electrons, okay. So the flow of electron is in this direction, so the current will be in this direction. So the drain current ID will be from drain to source, okay. So did you understand this concept? What we did, first we applied VGS. VGS will attract the electrons, so the inversion layer is formed. Now we have applied VDS. What VDS will do? Two phenomena that I have told. One is that it will make the depletion layer. The depletion layer will create the electric field in this direction, and that electric field will attract the electrons in this direction. And because electrons are getting attracted in this direction, the current will flow in this direction. Also, VDS is positive, and the channel is N channel, not N plus. The channel is N channel, so it has lesser conductivity and more resistance. Less conductivity and more resistance. So most of the applied potential will be developed across the channel resistance only. So the channel will have the most potential. Since the channel has lower conductance, it will have more resistance. Because of more resistance, by the potential divider rule, then more resistance will have more potential. If there is more potential, the electrons will feel more force and will go into the drain terminal, and the current will flow. So the drain current is from drain to source, okay. So you need to remember, in NMOS the drain current is from drain to source, okay. And now the VDS is small. Now what we'll do is that, so the drain current is flowing, so we can make a small characteristics. This is not the complete one. For small VDS, the relation is linear, okay. The current is flowing like this, and this is the condition when VGS is greater than VT. For VGS less than VT, there are no charge carriers, so no current is there. So we have made our device such that we have to apply some potential to get some current, okay. We have to, the output current is depending on the VGS value. The output current is depending on the input value. If there is no VGS, if there is no input, there is no output current. That means there is no output. If we have applied no input, no output current, no output. So the output is depending on the input, okay. Your output current is depending on the input voltage that we are applying. So that's why we use it in amplifier. That we will again see, okay. So yeah, so this is what is happening. Now what we will do, we will increase the VDS value. So the condition, yeah, like this also we can make, that I have already explained you. Just to make more clarity how inversion layer is formed. Okay, now we have more electrons that will go there and make the inversion layer. Okay, this is the inversion layer. So that we have already seen VGS less than VT, what happens and everything. Okay, yeah, so in summary we can write like the ID is greater than 0 for VGS greater than VT, and ID is less than 0 for VGS not less than 0. What I am doing, ID is 0 for VGS less than VT. What is VT? VT is threshold voltage. Okay, and that is positive for NMOS. Okay, now what we will do, VGS is greater than VT now, VGS is positive, VGS is greater than VT. Now what we will do, we will increase the VDS. Okay, if VDS is increased, this concept we have already seen. VGS is increased, reverse bias towards drain will increase, right? Reverse bias towards drain will increase. Good. Depletion width will increase. That means high electric field. That means more force on the electron. That means current increases, right? VDS increases, here the electric field increases because the reverse bias increases, electric field increases, more force on an electron, the current increases. That we have already seen. And at VDS equals to VDS sat, the current saturates. Now why so? Why at VDS equals to VDS sat the current saturates? Because the channel in drain side the channel is completely depleted of charge carriers. If we increase more VDS, the channel width get less, right? If we keep on increasing the VDS value, the channel width will get less, and because of that the channel will have lesser charge carriers and the current will be less. The same concept that we saw in the depletion type MOSFET. I have already explained this one, like why after VDS saturation the current saturates. Why the current saturates after VDS saturation, that I have already explained. Because the channel length decreases. If the channel length is decreased, there are lesser charge carriers. If the lesser charge carriers are there, there is more electric field. Okay, because of high potential at VDS, the electric field is more, so the current should be more, right? But because the charge carriers are getting decreased, the current is saturating. Okay, so but this is the ideal case. After that we will see that like this is not the condition in practical. In practical there is some slight increase in current. Why so? Because of the high electric field. You can already understand this concept, we will see that, but for now just see that the current is saturating. Okay, but this is not the complete concept. After that you will see that the current increases a bit. Okay, why does it increases? You can also think, because there is high electric field. The charge carriers are less, but the high electric field is getting what we can say, the high electric field is getting prioritized there. Means the effect of high electric field is high. So after VDS value gets increased, there is very high electric field that can attract electrons very fastly. So the current slightly increases. Okay, not much. Why not much? Because because there are lesser charge carriers. If charge carriers was more, and if the electric field was also high, charge carriers were more and electric field was also high, then the current would increase very nicely. That is in the case of this linear region. In this linear region, the charge carriers are almost the same because the shape is not the channel length is the number of electrons in channel are almost the same. Okay, but the electric field is getting increased. That's why the current is increasing here, and here the current saturates. I'm just repeating the same concept that I have already delivered. Nothing new. What is this value? That is VGS minus VT. This is linear region and this is saturation region. Okay, now what we will see, the VGS is greater than VT. Okay, VGS is positive, VDS is also positive. Now at different VGS what will happen? At different VGS what will happen? So if VGS increases, more electrons will be attracted in the semiconductor towards oxide layer. Right? When VGS is increasing, more electrons will be attracted in the semiconductor towards oxide layer. Right? If this positive voltage is more electron will come. If more electron will come, more current will be there. That means the current will also increase. Okay. So if we draw the characteristic now, this can't be seen. So if we draw the characteristics, so first it is the linear, then it saturates. But yeah, first it is linear, then it saturates. So here what is the case is that for more VGS value, the current is more. Like for more VGS value, the current is more. And till this point it is linear. After that it is in saturation. Okay. And the transfer characteristic ID versus VGS, before VT there is no current, then the current increases. Okay, that's how the current increases. Now if we talk about the VDS value in this one, so which one is higher? VDS 1 is higher or VDS 3 is higher? You tell me. There is also one hint is there, the green line you can see. VDS 1 is higher or VDS 3 is higher? VDS 1 is higher. Why so? Because if we have applied more potential, the current will be more. So at same VGS value, where we are having, this is the same VGS value for all three curves, right? For all three curves, VDS1, VDS2, VGS3, this VGS value is same. And at the same VGS value, we are getting more current in this curve. So VDS1 is higher than VDS2, than VDS3. At same VGS, we are getting more current for curve 1. At same VGS, we are getting more current for curve 1. So that means there is high VDS applied. Right? So this is the condition. Now we will see MOSFET current equations. So I hope you have understood this concept. Just repeat it once more, study it. It will be easy for you. Okay, thank you. Hello everyone. So now we will see MOSFET current equations. So before that you need to know what is W and what is L. So what is this? Like in MOSFET, first we have metal to which gate is connected, gate terminal is connected. So metal, oxide, and then semiconductor. In semiconductor we have this n channel formed. Okay, this n channel is formed in semiconductor. So we are taking that point, like let me show it in the diagram itself. So this we are considering, okay. So if you look from upwards, that will be channel width there. This is the front view. From here you are seeing, like here just I am seeing this part, this side of my hand. Okay, you are seeing from upward. If you see from upward, the channel is like this. Channel, there will be, this will be channel width, this is channel length. So this is channel length, and behind that channel width will be there. So that I have made. So that I have made the channel width, this is the channel length. Okay, and since here we get positive voltage, this is the positive voltage, so here we will have plus, right? And here we have electrons, so this is negative, we can see. So plus and negative and oxide in between. This is oxide, this yellow one is oxide, right? Plus negative oxide, metal plate and then semiconductor. So this is the case, right? Metal, the oxide layer, and then the semiconductor. So here we have positive and here we have negative. So this will give rise to some capacitance. So this will give rise to capacitance COX, that will be epsilon OX upon TOX. TOX is the capacitance per unit area. Okay, COX is the capacitance per unit area. Okay, so that we will see, that we will write once again. W is the channel width, W is the channel width, L is the channel length, COX is the capacitance per unit area. Okay, now we are writing current equation for linear or triode region. So what is the condition for linear and triode region? VDS is less than VGS minus VT, right? VDS is less than VGS minus VT. Yeah, here we have seen VDS is less than VGS minus VT. So this is linear, and after VGS minus VT, this is saturation. So the current equation, no need to see the derivation anywhere. You can see the derivation on YouTube or any source, you will understand it, but the derivation will not be used. No one will ask you. Okay, no one in any kind of analog profile interview, no one will ask you the derivation. So ID will be mu n COX W by L VGS minus VT into VDS minus VDS square by 2. Okay, and for saturation region, what is the condition? VDS is greater than equals to VGS minus VT. That means your ID will be mu n COX W by L VGS minus VT whole square by 2, and that 2 can come here. What we are doing is that after saturation the current saturates, right? The current saturates here. So what is the voltage of VDS here? What is VDS? VDS is VGS minus VT, right? I should write it here as well. Just make it like this. And this is VGS minus VT. This is VGS minus VT. So here in the linear region only, if I put VDS equals to VGS minus VT, just put VDS equals to VGS minus VT. This will be VGS minus VT whole square, and it would be VGS minus VT whole square by 2. So this current will come. And after this VDS value, the current will be the same. So it will be the same. So this current will not depend on VDS value. It is not depending on the drain to source voltage. Drain to source voltage is the output voltage. So the current is not depending on the output voltage. It is depending on the input VGS. Okay, but later on we will see it somehow depends on the output voltage. Just somehow. Okay, the channel length modulation that we will see. Okay, so yeah, that's it about the current. Then that's it about the current equations. So these two equations you need to remember. You just need to remember the first one. The second one you will remember by its own. So this is just a simple equation. Nothing difficult. And what is mu n? Mu n is the mobility of electrons. Mobility of electrons. Okay, charge carrier electron. Mobility of charge carrier electron, you might write. And this MOS concept you have already seen. Before VT there is no current. After VT the current increases. Before VGS minus VT the current increases linearly. After that it saturates. So that's it. That is all that you need to remember for analyzing the circuits. But the MOS physics you should also know, because some interviewer may ask you the question from MOS physics. Now we will see P channel enhancement type MOSFET. So the analysis will be the same. It will be covered in one video only. So we will see P channel enhancement type MOSFET. Okay. After that we will see few more concepts and the MOS physics will be clear to you. Okay. Thank you. Hello everyone. Now we will study P channel enhancement type MOSFET. Okay. So this is the P channel enhancement type MOSFET. Here instead of N plus we have P plus, and instead of P substrate we have N substrate. The same structure is there. You can analyze the device by your own as well. Okay. So one thing you must have understood here is that here the charge carriers would be holes, right? Here the charge carriers will be holes, and that will attract the and at drain we need to apply the negative potential, right? If we apply the positive potential at drain, the holes will not be attracted. So for attract the holes, we need to apply positive potential at the drain. So one thing you know is that VDS will be negative, VDS will be negative, or VSD will be positive. VDS will be negative, VSD will be positive. That means source will be at higher potential. For reference, for understanding the concept, we will take source to be 0 and then drain to be negative. But in case of PMOS, source is at higher potential, while in case of NMOS, the source is at lower potential and drain is at higher potential. Okay, so did you understand it? We will see the condition one by one, but the basics that you can understand by your own is that the drain potential has to be negative for attracting the electrons, and also for making sure that there is reverse bias between P plus and N substrate, right? So we will take the conditions one by one. VGS 0, VDS 0, nothing will be there, right? ID will be 0 ampere, right? VDS is negative now, okay? VDS is negative. For attracting the holes, VDS is negative, but VGS is positive. So let's see it here only. If this is positive, okay, and we have this here, right? This is N substrate. So this is what we have. So if we have positive here, so this positive charge will attract these electrons here, right? These electrons will be attracted here. So electrons will be accumulated here, right? And at drain we have negative potential. At drain we have negative potential. So these negative carriers will be attracted, and then we have the electric field. Okay. So that can attract, but this drain will not attract these electrons. Drain will not attract these electrons. Drain will only attract the holes. Drain, if there is negative potential, drain cannot attract the electrons. So this is the condition. Like there is depletion layer as well. In depletion layer as well, the electrons will feel the force and go towards the drain. But the drain will not accept it, because the drain has negative. And if you apply positive at drain, then the depletion layer will not be formed here. Here the depletion layer will not be formed. If we applied positive there, the depletion layer will not be formed, and strong electric field will not be there, and then the electrons would not be swept away. So both conditions are not getting met, right? You have to make both conditions. So you have to make both VDS and VGS negative. In NMOS we made both VGS and VDS positive. Gate was positive, drain was positive. Here the gate has to be negative and that drain has to be negative. So I hope you have understood this one. Okay. So you just have to relate it with the NMOS. Whatever the concept that we studied, it is exactly the same. Just relate it with the NMOS. The current will be 0 ampere. Here, if drain has no potential, VDS is 0, then one thing that you know is ID is 0 ampere, right? But we will see the analysis here because we have gate voltage negative now. Okay, so we have gate voltage to be negative. Okay, we have gate voltage negative now. So here, what do we have is that this is the condition, right? This is the condition. So this negative voltage, what they will do? They will repel the electrons, right? They will repel the electrons. So electrons will go downward. When now what we are doing is that, like many people will get confused, so I have to make a scale. This is the scale for VGS, and here we are 0. VGS, the gate is at negative potential. Now we are applying more negative value. Let us assume we are applying -1. Okay, at -1 this much layer is formed. Okay, we are applying -2, then this electron also goes, so this layer is formed. So if we are giving it more negative value, it is making the channel if we are giving it more negative, that will be good for us, right? So if like there is some threshold voltage, let us assume this is -3. At -3 we are having over channel of holes, not electrons, because negative charge will attract the holes and repel the electrons. So here we will have electrons, holes. Okay, so for VGS greater than VT, this is, let us assume this is VT. So this will be VGS greater than VT, right? And this -4 and all, this all would be VGS less than VT, right? So if VGS is greater than VT, here the VGS is greater than VT, right? So at this time the current will be 0. And what will be the condition? At this time you will not have charge carriers, you will just have the positive ions. But when VGS is less than VT, when you are giving more negative value, right? Instead of VT we will write VTP. When you are giving more negative value at gate, you are getting some current. So ID would be greater than 0, and at this point you will get not holes, right? And some positive charge, and some positive charge like this will be there as well. Okay, but you will get holes here and the current will be finite. Just relating it with the NMOS concept, nothing else. If VGS means so what you can understand here is that VTP is a negative value, right? I should write this is VTP. So here we can write VTP is a negative value, right? VTP is a negative value. So VGS is, if VGS is greater than VT, your current is 0. If VGS is less than VTP, your current is finite. So what else you can write here is that your VSG is less than mode of VTP. If gate to source voltage is negative, source to gate voltage will be positive because source is at higher potential. If gate to source voltage is negative, source to gate voltage will be positive. Let us assume we are having VGS equals to minus 2 volt that we are having. So what will be VSG? VSG will be 2 volt, right? Is this less than mode of VTP? What is mode of VTP? 3. Is this less than mode of VTP? Yes. So what will be the current? 0. So satisfying this condition. When people get confused, what we need to do is what did we studied in in NMOS? What did we study in NMOS? VGS should be greater than VT. We just need to replace over VGS with VSG and over VT with VTP mode, because VTP is a negative value that we need to replace. That's it. Just write it on some paper or somewhere else that when you are going from NMOS to PMOS, you just need to replace VGS with VSG, VT with mode of VTP, and VDS with VSD. Just you need to replace this. Okay, and this was just to make you understand. Okay, and in this one VSG is greater than mode of VTP. Just take an example. VSG 4 volts, that is greater than mode of VTP 3 volt. Okay, so that's how you can understand it. So for the current to flow, your VSG should be greater than, no, not for the current to flow. Here the current is not flowing. We haven't reached to the condition where the current flows. So, but we have reached to the condition where we have generated the holes. Now we just need to attract the holes. So for attracting the hole, what we will do? We will apply negative potential at drain. That's it. We have generated the holes now. We have generated the charge carriers. So now what we need to do? We just need to apply negative potential at drain and that will attract the holes. That's it. Right? So now what we will do? VDS negative, that is mole. And now your VGS is negative and that is less than VTP or more than VTP. If your VGS is less than VTP, your current will be greater than 0. And if it is less than VTP, then it will be 0. Did you understand this? This is the condition only. VGS is greater than VTP, then ID is 0. VGS is less than VTP, then ID is non-zero. VGS is less than VTP, then ID is greater than 0 and then non-zero. Or what you can write, or your VSG is positive and there are two conditions, greater than mode of VTP, less than mode of VTP. So if your VSG is greater than mode of VTP, then your ID will be greater than 0, otherwise ID will be 0. So that you have understood, right? Now VDS we have applied. If VDS is applied, then the current will be finite, that we have already shown here. Okay, because we have applied the negative potential at drain, that will attract the holes and the current will be finite. Okay, but the VSG value is the controlling. You have to apply VSG greater than VTP, then only the current will be finite. Here I have shown the current to be finite. This I shouldn't written. I shouldn't have written, because the current is not flowing here. This is the condition only, right? The current is flowing here when there is VDS is negative. When VDS is 0, you can't expect any current. When VDS is negative, then only you can expect a current. So this is the case here. What else we need to study in this case? Yeah, that's all I have written. Yeah. So now moving on to the next condition. So here now we are increasing the VSD value or increasing the VSD value or decreasing the VDS value. That means we are if VDS is negative, drain at negative potential. That's it. Okay. Yeah. So if VSD increases, or we can say drain goes more negative, more negative. Let us assume drain is -3. So what will be VSD value? VSD value will be VS plus 3, right? If drain goes -4, what will be VSD value? VS plus 4, right? VSD, VS minus VD. If VD is -3, it would be VS plus 3. If VD is -4, it would be VS plus 4. So if drain goes more negative, VSD increases, or VSD, sorry, VDS decreases. Then what will happen? If drain goes more negative, if this goes more negative, more holes will be attracted uh, because of the depletion layer formed, right? If drain goes more negative, more holes will be attracted. Okay. If drain goes negative, more holes will be attracted, and the current ID will increase. Okay. So you can make the curve now. ID will increase, and at a certain VHD value, the output saturates. Why does it saturate? That I have already told. Because of because the channel start getting depleted completely from from drain side. From drain side, the channel completely starts getting depleted, and because of that depletion, there are lesser number of charge carriers available. Okay, so the current saturates there. Okay, so at a certain VSD value, the output current saturates. The current ID saturates. So for for NMOS, what was the saturation value? VDS saturation. What was VDS saturation? That was VGS minus VT. So here just VDS. That was VDS. Here we will write VDS saturation. That would be VSG minus mode of VTP. Because VTP is a negative value and VSG and VSD both are a positive value. So that's how we need to write. I just told you to substitute. VDS will be replaced with VSD. VGS will be replaced with VSG. VTP will VTN or VT will be replaced with mode of VTP. So that's it. Okay. So if we make the characteristics, ID versus VSD we are making. Okay. ID versus VSD. Yeah. So initially it will increase. Then after that it will saturate. This region is called sublinear region. Okay. This is completely linear for lesser VDS value. After VDS is increasing, there we have sublinear region value, sublinear region, and then we have the saturation. Okay. And talking about VDS, so if VDS decreases, that means the VD goes more negative. If VD goes more negative, that means VDS decreases. If VD goes more negative, that means the current will increase. Okay, and what is this value? This is VSG minus mode of VT. No, not V. No, this is not this value. This is this value, right? VSG minus mode of VTP, because this is a positive value. gate is at lower potential, source is at higher potential, so that will be positive and mode of VTP will also be positive. So after VSG minus mode of VTP, the current saturates. So that's the condition. Okay, I hope you are understanding it. Just don't get confused. It is same as NMOS. Just replace VGS with VSG and VDS with VSD. Okay, and VT with mode of VTP. Okay, rest are all the same characteristics and everything. Okay, even the current equations are same. And why we are doing so? Because here the source is at higher potential and gate and drain are at lower potential. So we are just interchanging it. Okay. So now condition 6. That now what we will do? Not written here. What is the condition 6? Now we will increase VSG or we will decrease VGS and we will make VG more negative. That means if we are making VG more negative, that means we are decreasing VGS. We are decreasing VGS or we are increasing VSG. We are making VG more negative. So if VGS decreases, VSG increases, gate more negative, VSG increases. Okay, so if VSG increases, gate goes more negative. If gate goes more negative, if gate goes more negative, it will attract more holes. More holes will be attracted, so more current. Right? Current ID will increase. Okay, just the same concept like previous one. So this is the output characteristic, complete output characteristics. Okay, so first is ID versus VDS. Okay, so this we have already understood. Now this is VGS3. Yeah, upper one is VGS3, VGS2 and VGS1. Now you need to write the relation. How will you write the relation? Which one will be higher? So VSG3 will be lesser than VSG2 will be lesser than VSG1 will be lesser than VTP, right? Because VSG should be here, we will not write mode because all the values are negative. Why I am writing S? It should be VGS because the source is at higher potential. So VGS3 will be lesser than VGS2 will be lesser than VGS1 will be lesser than VTP. This is negative, this is negative, this is negative, this is negative. VGS3 is more negative. If VGS3 is more negative, then it will generate higher current because at gate you will need more negative value. Similarly, in this one, VSG3 is greater than VSG2 is greater than VSG1 is greater than mode of VTP. Since VTP is a negative value, like here you can see VTP is 3 mode of VTP is 3 volt. If VGS is minus 4 volt, that means VSG is 4 volt. If VGS is minus 5 volt, that means VGS is 5 volt. Right? So VGS is completely opposite. If VGS1 is greater than VGS2, that means VSG1 is less than VSG2. You are understanding? Simple mathematics. 7th or 8th class problem. Okay, just we get confused sometimes. So if we get confused, you just simply need to do this thing. VGS will be replaced with VSG, VT should be replaced with VTP, VDS should be replaced with VSD. While doing the circuit analysis, you will use this one. And if someone talks about the concept, you know the concept. If VG is more negative, more holes will be attracted, the current will be more. So if VGS goes more negative or VGS goes low or VSG goes higher, then we will have more current. Okay. If VDS goes more negative, that means if VDS decreases or VSD increases, then we will have more current, right? And at a certain value of VSD or VDS, the current saturates. If we further decrease VDS value, the current will be saturated, or if we further increase VSD value, the current will be saturated. That's it. Okay. So these are the curves, and now this is the linear region. Okay, and this is the saturation region. And if we make this point, that would be VSG3 minus mod of VTP. Okay. Now the transfer characteristics. Here I forgot to write. This would be VTP for a random VSD. I am a VDS, sorry. So similarly, if we are talking about VGS, that means gate is at negative potential. So for a certain VTP value, the current will not increase. After that, the current will increase. And we are talking about VSG now. So means source is at higher potential and gate is at lower potential. So till a certain value, till VTP, the current will not increase. After that, the current will increase. Okay. So you can understand this concept from here, right? So this is, and now talking about VSD, VSD2 or VSD3, which one is more? So VSD1 is more than VSD2, then VSD3. Why so? Because in the NMOS curve, VDS1 was larger. So here VSD1 was large. Here VSD1 is larger because at same VSG value, we are getting more current in VSD1. Okay. If VSD is more, that means the drain is at higher potential. If the drain is very high, the drain is at lower potential. If drain is negative, if drain is higher in negative, that means it will attract more current. So if there is more current, then VSD is greater than VSD2, is greater than VSD3. So that's it about the PMOS. So we have covered NMOS and PMOS completely now. If we are talking about definition, so what is VTP? VTP is the maximum value of VGS where the current flows in a PMOS, and this is minimum value of VSG where the current flows in a PMOS, right? Mode of VTP, minimum value of VSG where the current flows. Mode of VTP, maximum value of VTP. Here all the values are minimum, right? Here all the values are lesser than VTP, right? So all these values are lesser than VTP. So for all the values lesser than VTP, the current will flow. So the maximum value of VGS where the current flows in PMOS. After that, the current doesn't flow. While writing about the current equations, okay, if VSG is lesser than VTP, there will be no current, right? Because that will be in cutoff region, right? If VSG is greater, we are just doing the replacement. VDS is replaced with VSD, VGS is replaced with VSG, and VT is replaced with mode of VTP. So now we will write the equation mu P COX W by L VSG minus mod of VTP into VSD minus VSD whole square by 2. And third one I will write. So if this is the condition, VSG is less than mod of VTP. Oh, why less than? It should be greater than. Then only the current will flow. If VSG is greater than mod of VTP and VSD is greater than VSG minus VTP, then we will have saturation region. Okay, and the current equation will be ID equals to mu P COX W by 2L VSG minus mod of VTP whole square. VTP value will be always negative, mod of VTP will be positive. So that's it about the current equation. So this is the current equation. I hope you have understood the complete concept. Whenever we are talking about PMOS, we will just replace VDS with VSD and VGS with VSG, and VT will be mod of VT with mod of VTP, and rest all will be the same as NMOS. If they talk about concept, you can explain them the concepts as well. So that's the complete concepts of PMOS and NMOS. Then there are some known idealities. There is one more question, why oxide layer is used. So all these questions we will discuss now. Okay. So first we will see the PMOS and NMOS symbol. Then we will discuss those questions. Okay. Thank you. Hello everyone. Now we will see the MOSFET symbols. Okay. Yeah. So first symbol for this is for depletion type, enhancement type, and this is common for both. Both are these are commonly used. Okay. So for N channel depletion type, okay, this will be the gate terminal. Okay, this will be the drain, and this will be the source, and this is the body. Okay, when there is a sign from body, that will tell the sign of flow of electrons. Okay, flow of charge carriers, in NMOS. In NMOS, the flow of charge carriers, that means electrons will go from body to gate. At gate we apply positive will attract the electrons, right? So from body to gate, and here this is body is shorted with source, this will be drain. Whatever the terminal body is shorted, that would be source. So body is shorted with source, this is drain, this is gate. Okay, and the sign, what is the charge carrier in p channel? Holes. So holes, if we apply negative potential, apply negative potential, hello everyone. Now we will see MOSFET symbols. So for depletion type, enhancement type, and the symbols which are commonly used. Okay. So first we will see for N channel, then we will see for P channel. So for N channel depletion type, okay, N channel depletion type we are talking about. So this is drain. In in any MOSFET, the source and body are short circuited. This is source, this will be body. This is body, then this will be source. This is source, this is drain, this will be drain, and this is gate. Okay, this is gate. Okay, so now we need to see the sign now. Okay, so the sign will be always from P to N. It will always be from P to N. So in case of NMOS, the body is P. The bulk or substrate or body is P type, right? And the channel is N type. So from P to N, right? In NMOS, just remember the structure. Body is P type, substrate is P type, and channel is N. So from P to N. In case of PMOS, The body is N type, right? Body is N type, and the channel is P. So from P to N. Same here. Same this one. This is same. This is drain, body, substrate, gate, right? Gate. This will be source. This will be drain. But what is the difference? These line. Here dashed line, here solid line. Why solid? Because channel is already present. If the channel is already present, it would be a what do we say? Solid line. It would be a solid line. And if channel is not present, it would be a dashed line. Okay. Here we made the channel by our own, by applying the potential. So here we have dashed line, and here we have solid line. Okay. So that's how you can differentiate between depletion and enhancement. Now this is commonly used. Now what will be source, what will be drain? How will you tell? In case of PMOS, what was the current direction? In case of NMOS, what was the current direction? NMOS, from drain to source. In case of NMOS, electrons goes in the drain, so the current would be drain to source. And in case of PMOS, what will be the current direction? Holes goes into the drain. If holes goes into the drain, the direction will be the same from source to drain. So this shows the current direction from source to drain. So from source the current is getting out, and the arrow will be always on source side. Arrow will always be on source side. Just from drain to source, from source to drain, and this will be gate. Okay, so these two are the commonly used. This is also commonly used, but in digital circuits. So now how will you tell which is drain, which is source, which is what? Okay, so many people say that upper one is drain, lower one is source, upper one is source, lower one is drain. That's not how you analyze it. Okay, higher potential in case of PMOS, in case of NMOS, which one was at higher potential? We were applying VDS to be positive. VDS is positive. Source at 0, drain will be a positive. So in case of NMOS, drain was at higher potential. So that would be drain, and that would be source, and that would be gate. Okay. In case of PMOS, what was at higher potential? Source or drain? Source was at higher potential, because at drain we were applying negative value and source was short circuited. Source was grounded. And at drain we were applying negative value. So which was a higher potential? Source. So higher potential is source. Okay. Otherwise it is drain, and this would be gate. So in case of PMOS or in case of NMOS, you just need to see the higher potential. The one which is at higher potential, that would be source in case of PMOS, and one which is at higher potential in case of NMOS, that would be drain. So these are the MOSFET symbols. Okay, so these two are commonly used. Okay, this is for NMOS, this is for PMOS. So you should remember that in circuit analysis this is very important. Okay, now we will see some common questions like how many charge carriers are there in a MOS, like what is the need of oxide. Okay, and these already we have answered. So but many times again we will see why do we use MOSFET in enhancement or for amplification. It is written amplification, for amplification. Okay, so these answers we will see now. Hello everyone, now we will see some important question that can be asked based on MOSFETs. Okay, so first question is how many charge carriers are there in a MOS? You haven't studied BJT, but if you know a little bit about BJT, then you know that in BJT there are two charge carriers. If we consider NPN, so there are electron and holes. In PNP, electron and holes are there. So both electron and holes both electron and holes will be there. But in case of MOS, if we consider P channel, only the holes are responsible for the current to flow. If we consider N channel, only the electrons are responsible for the current to flow. But in case of BJT, both electrons and holes are responsible for the current to flow. So if they ask how many charge carriers are there in a MOS, only one. Okay, either holes or electrons. If they ask about BGT, you will say 2 holes and electrons. Okay, so this was one simple question. Now the question is, what is the need of oxide in that MOS? You see the MOS structure, right? There is metal oxide and then a semiconductor. So what is the need of that oxide, right? So what does that oxide do? So let's see. Let's consider a NMOS. Okay, let's consider an NMOS circuit. Okay, so this is NMOS. So in NMOS, what we do? We apply positive potential, right? And because of this positive potential, negative charge comes there, right? If this oxide wouldn't have been there, if the oxide would not be there, this negative charge would have crossed the layer, right? There is negative charge on the semiconductor. If instead of oxide we would have put a metal, then this negative charge would have crossed the layer and would have reached to the metal. So negative and positive will be neutralized, right? If oxide is not there, this negative charge will reach the metal, so the inversion layer will not be formed, right? Whatever the charge comes, all the charge will go upward, 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 and there will be a current flow, right? There will be a current flow, but there will not be any inversion layer formed. Current flow in upward direction, not in like this from source to drain. There would be a current in the upward direction, but since oxide is there, so there will not be any current. If we had some metal or anything, if we are applying some positive voltage and then we are getting some negative in the semiconductor surface, if the negative charge is getting reached to the metal, then the inversion layer would not be formed. So this oxide prevents this negative charge to go to the positive charge, this negative charge to go to the metal. So if the oxide would not be there, the negative charge on semiconductor would have reached the metal plate and inversion layer would not be formed. Let us consider this is Ig. Okay, since SiO2 or oxide is there, Ig equals to 0 ampere. Input current in the MOSFET is 0. Okay, if the oxide wouldn't be there, the negative charge on the semiconductor would have reached the metal plate and inversion layer would not be formed. Okay, and since SiO2 is there, the Ig current is 0 ampere. So this negative charge is not reaching the positive metal plate. Okay, now why do we use MOSFET in enhancement of mode for amplification? That we have already seen, right? I have already answered this question many times. Why don't we use the depletion one? That I have already answered. You can check the video, because the channel is present there and the output is not depending on the input. Even if the VGS is 0, VG is the input, right? Drain is necessary for having the current. That is not your input, right? You can't apply input at drain. You are getting current at drain, so that is your output, right? VDS will be your output because you are getting the output current there. Your input would be VG voltage, because that is the controlling one. Okay, in case of depletion time MOSFET, if you had applied VGS equals to 0 and some VDS, okay, then we are having some current. But here, if VGS is 0, you will not have the current. Till VGS is less than VT, there will be no current. So in enhancement type MOSFET, VGS less than VT or VSG less than VTP, there is no current. The output current ID depends on the input voltage VGS, and this is what we wanted to make, because when we studied about that, when we studied in the first page, like why we are making the MOSFET, why we are making the MOSFET. So there we studied that we need to build an amplifier and you need a dependent source, and that dependent source which is dependent on the input. So this will be gate, this will be source, this will be VGS, this will be ID. Okay, so the ID current, we will see this, we will see the small signal model. So here what you could see here is that the current is depending on the input value. So this is what we wanted to make, and we are successful in that. Okay, that's why we use enhancement type MOSFET for amplification. Okay, like this is your VGS, here this is your V in, this is your drain current, this is your gate, this is your source, this is also your source. Okay, this is your drain, right? Now from drain to source current is not there. Yeah, that's fine. From drain to source is current there. From drain to source we have the current flow in case of NMOS, for NMOS, right? This is the drain current ID and this is RL. Okay, so this drain current ID is directly depending on the input. Okay, so that's why we use the MOSFET enhancement. That's why we use enhancement type MOSFET for amplification. Okay, and now we will not now, we will later on see that we use enhancement type MOSFET also in only saturation region for amplification. Okay, not in active region. Why only in saturation? That also we will see. First we have seen we don't use depletion type, we use enhancement type. Then we will see we use it in saturation region. Okay, now we will talk about the channel length modulation and body effect. Okay, so after that your MOS physics will be completed. Okay, hello everyone, now we will study about the channel length modulation. Okay, so ideally what we see here in that in the transfer characteristics is that after VDS is, we are considering NMOS. Okay, consider NMOS. So in the transfer characteristics, we have seen that when VDS is greater than a certain value, when VDS is greater than VD saturation, then the ID current ID saturates. Okay, the ID current is saturated, the ID current is constant. But practically what we see here is that when VD is greater than VD saturation, ID increases slightly. Now why does that happen? You can estimate it as well. I have already told it as well. Like when VD is greater than VD set, what happens is that your channel will look something like this, right? And these are your charge carriers. And this is, here we have depletion region, right? This is plus, this is minus, this is plus, this is minus, this is plus, and this is minus. So what reason I told to, what reason I told for the current to saturate? What was the reason that I told? I told that the current saturates because the number of charge carriers are less in the channel. Look, the number of charge carriers are less in the channel. But what happens is that if we furthermore increase VDS, this electric field becomes very strong because of high VDS, high depletion, high depletion, that means high electric field, that means electrons are swept with, are swept away with high speed, and the current increases slightly. So here that electric field phenomena becomes a bit dominating. The electric field becomes so strong that they swept away the electrons with very high speed, and the current increases slightly. Okay, so practically we see that the after the saturation voltage, the current is not the same. It is increasing a bit, just a bit. Okay, not too much. It is increasing slightly. Okay, so what we can see is this ID versus VDS curve we have. Okay, and that's where we see the saturation. This is VDS FET. This is the ideal one, right? And this is the practical one. The current is increasing, and if we increase the graph goes here like this. So at VDS equals to VA, the current ID is 0 ampere, right? And this VA is known as early voltage. So in case of NMOS, that negative value of VDS where the current becomes 0 voltage, that is known as early voltage. You may write it. I will say it once again. In case of NMOS, that negative value of VDS at which ID becomes 0 ampere, considering the channel length modulation is there. The channel length is modulated here, right? This channel length is modulated. The channel length becomes low, becomes a bit short. Before that, the channel was this, complete this, but now the channel length become has become short. So considering channel length modulation, when the negative value of VDS at which the ID currents becomes 0, that is known as early voltage. Okay, so you may write it in your notebook. Okay, now since the drain current is not constant, the drain current is depending on the VDS value. So the drain current in saturation region is given by ID equals to CLM, I will write, and furthermore I will write it ID only. That would be equals to mu1 CUX W by 2L VGS minus VT whole square. This is the part. This part is the same. Also, we will have some part 1 plus lambda VDS. Okay. So this complete part is the same, right? So I can write ID sat plus 1 plus lambda VDS. What is ID sat here? The saturation current without channel length modulation. Saturation current without channel length modulation. Okay. So the drain current in saturation region will change. The drain current in triode region will be the same. What was the formula of drain current in triode region? Mu n CUXW by L bracket VGS minus VT into VDS minus VDS square by 2 bracket closed. So that was the formula for drain current in triode region. But in saturation region, since the curve is not flat, the current is not constant, the current is depending on the VDS value. So the formula becomes mu n CX W by 2L VGS minus VT whole square into 1 plus lambda VDS. The current for triode region is the same, but the current for saturation is different. Mu n CX W by 2L VGS minus VT whole square into 1 plus lambda VDS. Okay. And what is lambda? We call it channel length modulation parameter. CLM, channel length modulation parameter. Okay. What would be its unit? You can see here voltage inverse, because this is unitless, so it has to be voltage inverse. Okay. So I hope you have understood all this. Okay. Now what you can see is there that ideally the current is constant in saturation region, right? The current is constant in saturation region ideally. This is the current mu n CXW by L VGS minus VT whole square. Okay, mu n CXW by 2L VGS minus VT whole square. So what is 1 upon lambda 1 upon del ID upon del VDS? What is 1 upon del ID upon del VDS for ideal situation? For ideal situation, that is 0, because it is not depending on the VDS at all, right? All this is constant. So 1 upon del ID upon del VDS will be 0. So the output resistance is finite. Infinite. Infinite. The output resistance is infinite for ideal case. But when we consider, but practically considering channel length modulation, how this formula came, that you don't need to know. Okay, the derivation is very easy for this one, but no need of derivation. How this formula came, there is no need to know that. Okay, but the derivation is very easy actually. Like, yeah, I told to write one more thing here. If this is the length L, so this much length we call delta L. Okay. This much length is delta L. This is L, this is delta L. Okay. Actually, this is not L. L would be the complete channel length. That would be L. Okay. This would be L. And this would be delta L. So L minus delta L would be the channel length now. Okay. And by that you can simply derive it, but you don't need to go to the derivation. This is the current formula. And now we are considering the practical case, considering channel length modulation. Your ID is becoming ID sat. ID sat is the drain current without saturation. Sorry, the drain current ID sat is drain current in saturation region without channel length modulation, without considering channel length modulation. So now what will happen? Del ID upon del VDS. It would be ID saturation into lambda. So your RDS would be 1 upon del ID upon del VDS. That would become 1 upon lambda ID saturation. Okay. So this is the value of RDS. Black. Yeah. So this is the value of RDS. So the output resistance is finite. Okay. And one more thing is there, that at VDS equals to VA, ID becomes 0 ampere. At VDS equals to VA, the ID becomes 0 ampere. So just put ID equals to 0 here. So what will be the value of VA? VA would be minus 1 by lambda. Then VA would be minus 1 by lambda. Okay. So at VDS equals to VA, the ID current becomes 0 and the VA would be minus 1 by lambda. Here you put VDS equals to VA and ID equals to 0. So VA would be minus 1 by lambda. Okay. So I hope you have understood the concept. When VDS is greater than VDS set, the current practically the current doesn't saturate because of the high electric field. The electron feels very high force and the current increases a bit. The current increases slightly, and because of that, there is a finite output resistance in the op-amp. Finite output resistance in the MOSFET, and the value of that is 1 upon lambda ID set, where ID set is the drain current in saturation region without considering channel length modulation. Okay, so it is simply 1 upon lambda mu n CoxW by 12 VGS minus VT whole square. So this is the formula, but in short we write it like this. Okay, and in many question RDS value will surely be given, or lambda value will be given. You can find RDS value. Okay, yeah. So I should have written the small signal output resistance. You will understand what is small signal. So the small signal output resistance is finite. Okay, now we will see the body effect. Now we will see what is body effect. Okay, thank you. Hello everyone. Now we will see the body effect. Okay, this body effect we will see. So ideally, I have told you that VSB is always 0. We always short circuit source and body. Source is taken as a reference. That's why we make it ground. And also we short circuit source and body. So if source is ground, why source is always ground? Because it is taken as the reference. Okay. So source we make ground and source and body are shorted. So why do we always short source and body? That would be the question. So what will happen if you don't short circuit the source and body? So that is very important concept. Okay. So many times question are asked from this topic. Okay. So let us consider an NMOS. Let's consider an NMOS circuit. Okay. So this is a simple NMOS, N plus gate terminal source. Now we are taking VSB as positive. We are applying a positive voltage between source and body. So what we can say, if source is at 0 potential, so body would be at negative potential, right? If source is at 0, then body would be at negative potential. So we are making VB to be negative or VSB to be positive. Now what will happen is that now this is negative, right? This is negative and this is positive here. This is positive and this is negative. So here the for reverse bias is getting increased. Reverse bias across across source terminal increases Actually, the reverse bias across the drain terminal also increases, but that's not a matter of that's not. But we don't need to think about it now. We just need to think about the source terminal here. The reverse bias across the drain terminal also increases. Okay. So when VSB was 0, this drain was positive and gate was positive. We have already applied the potential there at drain, at gate. So when VSB was 0, this was the depletion region, right? This is the depletion region. This was the depletion region, right? When VSB was 0. Now since the reverse bias has been increased here, the depletion also here as well. Okay. So the depletion layer will increase, right? This is P substrate, is N plus substrate. Because of this positive potential at N plus side, there was some depletion region. That how depletion region is formed, that we all have already seen. So now that this depletion width increases. Now this depletion width is increased when VSB is positive or VB is negative. Now the depletion width is increased. Okay. So if the depletion width is increased, what is happening here is that we have plus here and minus here. Plus here and minus here. If that depletion width is increased, this electric field is strong enough. Electric field near the source side increases, right? Right? VB is negative. If VB is negative and VS is positive, the reverse bias across the reverse bias near the source terminal increases because of the high reverse bias. The depletion region increases. Okay, because of the high reverse bias, the depletion region increases. If the depletion region increases, the positive and negative ions will be increased, and there will be high electric field. So if an electron is coming, like this is the direction of electric field, right? And this is the source. From source, one electron is coming. So this electron is coming here. Okay. Electron will feel the force in opposite direction. So the electron that is coming from the source terminal, that will be swept back to the source terminal. So now you have to apply more Vg value to get the current. Like to break this electric field, you have to apply more Vg value to get the current. That means your threshold voltage will increase. Did you understand it? We applied base voltage, not base, source to base I am saying. For the complete time I am saying base. Body, oh yeah, okay, yeah. So we always short circuit source to body, but now we are applying source as positive voltage and body at negative voltage. Because of that, the reverse bias increases, the depletion layer increases, and because of that there is high electric field. So the electron that is coming from the source terminal, that feels the high force to the source terminal back. Okay. So to break this electric field, you have to apply more VGS. And if you need to apply more VGS, that means your threshold voltage will increase. Okay. So electric field near source side increase. To get the electron through the channel, you need high Vg. That means your threshold voltage increases. Threshold voltage Vt increases. Okay. So to break this electric field, you need to have a high value of Vg. So your threshold voltage will increase. Okay. And your threshold voltage increases by this formula that you don't need to remember. no need to remember this formula. You can remember, okay, this is not that tough. Like what is that formula of 2πf? That all that you don't need to remember. What is VT naught? That is ideal threshold voltage. This is ideal threshold voltage when VSB was 0 volt. Okay. This gamma, what we say, fabrication process parameter. Fabrication process parameter. And what is this 2πf? This 2πf is, this is equals to πs, and that we call it surface potential. Okay, so this 2πf is surface potential. Okay, now we will see one more case where we will apply VB to be positive. Okay, now your VB is positive or VSB is negative. So now what will happen? Okay, now this is negative and this is positive. So now the forward bias increases, right? The forward bias increases, the depletion layer, the depletion width goes low, and because of that there is a high current flowing in the MOSFET, and the device burns out. Look, the source is negative and body is positive. So here the forward bias increases, right? Here also the forward bias increases because, okay, this is already positive, so not much forward bias increase, but the forward bias increases a bit, right? No, it doesn't increases because the drain is at positive already, and you are applying positive voltage as at the forward bias will increase, right? So if the body is getting, if the P substrate is getting positive voltage, that means forward bias is getting increased. That means the depletion width is getting low. So I guess I should use third pen, different color, maybe this one. Okay. So what do we see here is that the forward bias is getting increased, so the depletion width gets low. Okay. Forward bias increases and depletion width goes low. Okay, the forward bias increases and depletion width goes low. So the forward bias increases and depletion width goes low. Because of that, a huge amount of current flows and the device burns out. Device burns out. Like many people say that if VT is positive, if VSB is negative, that means if VB is positive, then the threshold voltage will decrease. Is that right? No, it's not right. If VB is positive, then here the reverse bias, here the forward bias is getting increased, right? That means reverse bias is getting less. That means the depletion layer will be less. The effect of electric field will be less, right? So you can't say that you need to apply less gate voltage. If this was the case, we would have already put VB to be positive every time, but we don't put VB to be positive every time. We always take VSB equals to 0 volt. Why so? Why do we always take VSB equals to 0 volt? Because negative potential will increase the threshold voltage, while the positive potential can burn out the device. Okay. So if they ask you simply why source and body is shorted, so in case of NMOS, if VB is negative, Because of the then you can draw this diagram and you can tell them that there is high reverse bias, and because of that depletion layer will be increased, and because of that high electric field you need to apply more Vg value so that you can pull out the electron from source. Okay, so the threshold voltage will increase, and in case of Vb equals to positive, the depletion layer will be very less, and because of that because of that if the depletion layer are less, like this is the depletion layer, if the depletion layer is less, the electrons will cross the depletion region very fastly. The electron will cross the depletion region very fastly, and a high amount of current will flow and the device will burn out. So that's why we always take VSB equals to, that's why we always take VSB equals to 0 volt. So these two are the regions. Okay, so this is the body effect. So now your MOS physics is completely over. Every aspect has been cleared. Okay, from depletion type MOSFET to enhancement type MOSFET, and then N channel, P channel, MOSFET signal, basic questions, channel length modulation, body effect, everything is cleared. So no other question can be asked from this topic if you have seen those previous videos of MOS physics. So this is the complete analysis of MOS physics, and if I have uploaded it on YouTube, then please try to share it. Okay, like many people find it tough, like where should we study the MOS physics from, and they find the topic very tough. This is the toughest topic of analog electronics that I will say. This is included in actually EDC, but but an analog designer should always study this MOS physics. Okay, so just try to share it your batchmates so that they can learn it as well. Okay, and if you want to purchase my basic electrical course, that also you can purchase it from my site, and if I am uploading it on YouTube, then I will also put the link. So from there also you can purchase the basic electrical course. So by basic electrical course and this analog electronics course I will launch very shortly. So from there you can prepare for placements. Okay, thank you.